Imagine vast rivers of ice, slowly but powerfully carving landscapes, carrying immense loads of rock and debris. These ancient forces create some of Earth's most striking geological features, leaving behind clear signatures of their journey. One such fascinating signature is the medial moraine, and these distinct ridge-like features develop on glaciers primarily when two separate glaciers, each carrying its own lateral moraines, merge together. When these ice streams coalesce, the debris formerly at the edges of each individual glacier is brought into the center of the newly combined, larger glacier. The formation process is a direct consequence of glacial dynamics and the erosional power of moving ice. As a glacier flows, it plucks and abrades rock from the valley walls and floor, accumulating this material along its sides, forming what we call lateral moraines. When two glaciers from adjacent valleys converge, their respective lateral moraines are trapped between the two ice masses. The forward movement of the combined glacier then carries this consolidated ribbon of rock debris along its surface, often for many miles down valley. This material is primarily superglacial debris, meaning it sits on top of the ice. To understand this better, picture two streams of ice, each like a conveyor belt, moving independently. Each conveyor belt has its own pile of rocks on its outer edge. When these two conveyor belts merge into one wider, faster-moving belt, the two piles of rocks meet and become a single, linear pile running down the middle of the new, larger belt. Observing medial moraines can help scientists map ancient ice flow patterns and reconstruct the history of glacial advances and retreats. They are excellent indicators of past glacial confluence events. What makes medial moraines particularly insightful is their role as direct evidence of glacial merging events, distinct from ground moraines, which are deposited underneath the ice, or terminal moraines marking the farthest extent of a glacier. These striking linear bands of rock on the ice surface provide a visual record of where different ice masses converged, acting like natural flow lines within the glacier itself. They essentially fossilize the point of intersection. Ultimately, understanding how medial moraines develop provides crucial insights into the complex mechanics of glacial movement and the profound role these colossal ice masses play in shaping our planet's geomorphology. They highlight the dynamic interplay between ice, rock, and gravity, revealing stories of ancient landscapes and climate shifts embedded within their rocky stripes.